So I'll be talking about the DIRBE reanalysis, which is something that is significantly less mature than either the WMAP, LFI, or spider analysis that we were just talking about. But essentially, I just gave the DIRBE reanalysis the subtitle of recovering some ancient dust measurements for modern microwave data analysis. So for those of you that aren't familiar, DIRBE was an instrument on the COBE satellite and took full sky observations from the start of December 1989 all the way up until my birthday in 1990. And it observed in 10 bands between 1.25 and 240 microns, so in the infrared and far infrared. Why do we care about DIRBE? Well, it's fantastic for really helping to nail down this tail end, the wing tail of the thermal dust spectrum. In addition to that, it also has probably the best full sky observations of the zodiacal emission, which is something that is definitely something we need to be thinking about for the future. So for an example, here's what DIRBE looks like at 60 microns. So you can clearly see the galactic plane right in the middle. For dust emission, but also this zodiacal emission along the ecliptic here gives you a very distinct view on the sky. So talking about the DIRBE data itself, we were able to just pull the DIRBE data right off of Lambda. What we've decided to use is the calibrated individual observations. We asked for the actual raw data themselves, and we were told by the people working at Lambda, you don't want the raw data, you want the calibrated individual observations. And after looking at the instrument, it seems like there's a lot of work that goes from the raw data to actually getting these calibrated individual observations. So that's where we've started for now. This is a zoomed in on a very short time chunk of what the DIRBE CIOs look like. So DIRBE sampled the sky 8 times a second, relatively low sample rate. And so here's exactly what it looks like over just, about an hour and a half of observations. So the data details itself, DIRBE is a fantastic test case for getting into Cosmoglobe because it's very light. There's 81 gigabytes of data total. There's about 5 gigabytes a channel. Which most modern laptops can easily handle to hold all of that memory at once, at least one channel. The data that we're using is pre-calibrated, which may be something we have to solve later on, but it's nice for now. Unfortunately, the data is old, and as a result, it was all stored in quad cube pixelization, which we'll talk about. There's also some interesting things with the flags, since COBE flew in a low Earth orbit as opposed to out at L2 like WMAP or Planck. There's contamination from radiation zones. And then there's also polarization data in the lowest wavelength bands. So the quad cube is something some people are probably familiar with. It's essentially just a way to represent pixelization on the sky from a 6-face cube, as you can see on the right. We are able to assimilate this into the Cosmoglobe framework by using some ancillary data that's available on just on Lambda itself, which allows us to put these quad cube pixels into lon lat, galactic lon lat, and then we can move that to helipix pixels. The radiation zones that I was talking about, it's flagging that seems unique to COBE. The spacecraft itself actually passed through the radiation zone, so you can see in the right-hand plot here the actual glitch rate at I think it's 240 or 100 microns as a function of the grid over the Earth. So you can see both the Van Allen belts at the north and south at about 50 degrees, as well as the South Atlantic anomaly. So these things are something we need to take into account when looking at the DIRBE data itself. DIRBE actually does have polarization data. So looking at the plot on the right, you can follow as the light comes in. Some of the light gets passed through these polarizers at the bottom. And that's only available for the 3 lowest bands at 1.25, 2.2, and 3.5 microns. Each of them have 2 polarimetric detectors. Because of these polarimetric detectors, the way that they're designed, they're actually orthogonal to each other, which means you're only allowed to measure 1 Stokes parameter at a time. So it was kind of difficult to figure out what the data was supposed to look like in polarization, but there was one publication, which you can find here. And you can see the top left plot is the DIRBE scan path. And then for Stokes Q and U, those second two plots on the left-hand column, you can see that you're not actually able to cover the entirety of the sky that is scanned at that time in Q and U because of these orthogonal detectors. So they've defined this, this new parameter, which they called YB and YC, which you see in the top right, which essentially just states how much of your total signal that you're getting is polarized. And you can see on the right here their estimates for this. We've run this through a simple bin map maker and looking at what the sky looks like here at 1.25 microns, 2.2 and 3.5 microns. It's not entirely clear what we can really pull away from this at this time, but these maps are in ecliptic coordinates. You can see the galactic plane as a big scar through here. So it looks like there is some actual real data to get dug into. Just from the raw CIOs that we've had run through a simple bin map maker, which you can just do on your laptop, we were able to make some preliminary difference maps compared to the actual DIRBE products as you can find them on Lambda. And you can see that overall the agreements are really quite good, but you can see some what looks like pixelization errors, and there's probably some planet flagging and other things that haven't been taken into account that we really need to dig into. But it looks like there's a lot of interesting stuff to be done moving forward here. So really what comes next? So a Commander 3 module has just been started, and we're essentially just building it off of the Lightbird module that we currently have, and hopefully we can expand this thing further, although this has been very early stages. We have to do some flagging tests. We haven't looked at all at noise properties, so it's interesting to see what kind of noise that they've actually taken out of the data, or if they've actually only calibrated it, what to do with that. Data anomalies are something to look at. Metin will be talking about in the next plot, or in the next talk, about some pretty obvious, looks like there's some issues with the planet flagging. And then there's also component separation, which is the most interesting thing for me personally, and zodiacal emission modeling and how we can move forward with that. As always, thanks for the funding. And if you have any questions about DIRBE, please just let me know, send me an email, and love to have anybody help join. So thanks.